All right. So the difference in pure imaginary numbers and complex numbers is that we have a real number portion that's added to the imaginary portion. So you look at that first box there. It says the complex numbers. Consider this number 5 plus 2i. Because 5 is just a regular real number, and 2i is a pure imaginary number. When you put those together, then that forms a complex number, is what that combines to be. Standard form for a complex number is going to be a plus bi. So all of our answers, when it's just doing operations with complex numbers, need to be written in this order. It's kind of like descending order we did with polynomials. You have to start with the highest power of x. Everything that we do with complex numbers needs to be written in this order at the end, where you have the real number first, and then the imaginary part, the part with the I involved. So that is called standard form. Again, this is the real part. So if we refer to the real part, and then this is the imaginary part. So standard form for a complex number, if we do it on the graphing calculator, it's going to automatically put it in that form anyway. But we just got to make sure that when we do it by hand, we're doing that too. Okay, so we're going to start out adding and subtracting. Really easy concept here. It's just like when you added polynomials or like terms. That's all this is. Adding, subtracting like terms. So on the first example, you got negative 11 plus 3i plus 9 plus 2i. That's two complex numbers, but you're just putting like terms together. So what is the like term to the negative 11? The 9. So we're going to put negative 11 plus 9 is negative 2. And then we're going to say positive 3i plus positive 2i would be positive 5i. And we're done. It really is that easy. It's nothing more than that. Absolutely, that's all there is to it. Now, I never do adding and subtracting complex numbers in the calculator, but I'm going to show you how so that you know how to type in the complex number out of that. So with your graphing calculator, I'm just here. I'm going to get on the regular calculator screen, clear that out, okay? Make sure we're in the right mode. So if you borrowed one from me, hit mode, or if yours is, just make sure yours is in the right mode. Hit mode, go down to the line that has the real, and then a plus bi, and then r e to the I theta, and make sure the a plus bi is darkened in. Hit mode and go down to that line, make sure a plus bi is darkened in so your calculator knows that's what you're doing, okay? If you haven't reset your calculator since last week, it should already be there, okay? A plus bi mode, second mode to get back to the regular calculator screen, or you can turn it off and turn it back on, whichever way you want to do it. And then I'm going to type in those two complex numbers. So I'm going to do parentheses, negative 11 plus 3. And then to get the I, how do I do that? Second decimal point. And I'm going to close the parentheses. I'm just going to type it in exactly like they've got it written on the problem. And then plus parentheses 9 plus 2i. Second decimal point for the I. Hit enter. Woo. All that time it took us to type it in, we'd already done the problem. Okay. I don't do this in the calculator very much because it's too easy to just do without the calculator. Like terms, put them together. But know that you can check your work with the graphing calculator. Okay. And when we take a quiz over this, you will be able to use your calculator, so you can check and make sure that you got it right before you turn it in. Don't miss it because of that. But know how to do it without the calculator, because that's going to be on the non-calculator portion of the benchmark, on the non-calculator portion of the EOC, and then it takes you longer to type it in than it does to do the work on ACT if they give you a problem like that on ACT. I've only seen a couple of practice ACTs that had that kind of easy problem on it, but they do put it on there periodically. All right, I'm going to skip down to number 3 and do a subtraction problem. I'm not going to do every example today. So 7 minus 2 would be 5. Negative 2 minus 6 would be what? Negative 8. And again, I could check that with the calculator. It is very important that you use parentheses, especially in the subtraction problems. The addition problems, it really doesn't matter if you use parentheses or not. But the subtraction problems, it does matter. Okay, so I'm going to type in that problem 7 minus 2i, close the parentheses, minus parentheses 2 plus 6i. 5 minus 8i. Or 5 plus negative 8i, whichever way you want to write it. It's the same thing. All right, easy stuff. So a subtraction, that's all it is, putting the like terms together. Number 4 there, you just got extra like term. Only difference. If I did that, I'd have positive 6i and minus negative 1i would be 7i, plus negative 3i would be 4i. Now I got to get the like terms with the real numbers. This is tricky right here. That's a negative 14 plus 5, which should be negative 9. And I put it in the right order there. Real part first, imaginary part second. If you type that straight into your calculator, exactly how it's written, that's what it'll crank back out. Those sign mistakes, most common mistake in math, no matter what kind you're doing, whether you're from 4th grade all the way up to now, it's going to be the most common mistake. So be careful on the signs out of that. All right. So addition, subtraction, you can do it on the calculator. I don't usually do that just because it's too easy, and I can do it without that. Multiplication, also pretty easy. One thing that you've got to keep in mind is when I multiply these out, it's just like if I multiply x times x. When I multiply I times I, what do I get? I squared. So when I multiply this out, that's going to be 2i times 8, which would be 16i. And then 2i times negative 3i would be negative 6i squared. We've got to remember that little chart. Remember, we talked about that last week, that the definition of I is the square root of negative 1. Then I squared turns into negative 1. And then I cubed turns into negative I. And I to the 4th power is positive 1. And anything bigger than that, it starts repeating. And we divide by 4 and get the remainder. So on this one, I've multiplied it out. Now I'm going to simplify it. So what can change in this problem? The I squared is going to turn into negative 1, right? So that's 16i minus 6 times negative 1 is really what's happening. So what's that change that 6 to? It's a negative 6 already. So it changes it to positive 6 plus 16i. Okay. So again, I'm rewriting the answer in standard form for a complex number. Now, maybe it's a little bit more helpful to check this one with the calculator. So I just type it in just like it's written, and it cranks it back out the same way. Okay. Again, though, you need to be able to do this by hand for the non-calculator portion of that, and also for these quick and easy problems. It takes longer to type it in than it actually does to do the work, if you'll know how to do it. Let's do number 6. Multiplication is a little bit more difficult. So what happens when you distribute that negative I? That turns it to a positive 2i, negative 10i squared. I squared does what to this? So a double negative makes it positive 10 plus 2i. Anytime and you see that I squared, that's going to change the sign of whatever number it's beside. And because it was beside a minus 10, it changed it to a positive 10. I squared is always going to do that. Now let's get into number 7 there. We've got two standard form complex numbers, and we're going to multiply them together. This is just like what you did in Algebra 1 when we gave you a problem that said x plus 3 and x minus 2, something like that. You just distribute each piece across the across the parentheses. We're doing that and getting something left. That's what we're going to do here. We're going to multiply 7 times 4, 28. 7 times negative 1i would be negative 7i. I times 4 would be 4i. Then I times negative I is negative I squared. And we're just distributing each piece across the parentheses. And then we're simplifying. Like terms together, change any of the I squareds. So 28 minus 3i. What does negative I squared turn into? Positive 1. I squared is the same thing as minus negative 1. Minus a negative 1 is going to turn into plus 1. And now we can finish it off. 28 plus 1 is 29 minus 3i. If you're unsure of yourself on that, use the calculator to check it. Okay, type it in just like what it's written. It's written parentheses 7 plus I, close parentheses, open up another set, 4 minus I. 29 minus 3i. What do you know? That's what I got when I did it by hand. Okay. Let's do number 8. Same story. 2 times negative 5, negative 10. 2 times negative 3i, negative 6i. And then multiply negative 4i. It'd be positive 20i. Positive 12i squared. Combine like terms and convert the I squareds. That's what we need to do. So like terms, those two in the middle, be plus 14i. What does 12i, positive 12i squared is going to turn into negative 12. And now like terms for that would be these two together, which would be negative 22 plus 14i. Again, you can check that with the graphing calculator. It will work it out and get it in standard form. As long as you can type it in just like it's written, it can work it out. Okay, as long as you're in the right mode. Look at number 9. Sometimes we forget what that means. What's it mean to say 6 minus 2i squared? 6 minus 2i and then another 6 minus 2i. That's what it means. Don't make the mistake of just squaring the 6 and squaring the 2i. That's not all that there is. A lot of people want to go, oh, I just square both things inside and get 36 plus 4i squared, which is not correct. You'll miss the middle piece. So we're going to write it out twice and multiply. 6 times 6 is 36 minus 12i minus another 12i plus 4i squared. It does have the 36 and it does have the 4i squared, but if you skip this multiplying it out, you're going to miss that middle term. And that middle term does not cancel out. It becomes 36 minus 24i. And then what does minus 4? The I goes away. You do that I squared. So 36 minus 4 minus 24i. One of the niceties of the graphing calculator is that you could type in 6 minus 2i in parentheses, and then close those parentheses, and then hit the squared button, which is up and to the left of 7. And you don't have to type it twice. It cranks it out to be what we found by doing it by hand. And again, multiplying, adding, and subtracting is most likely going to be on the non-calculator portion of benchmark, EOC, and well, there's not a non-calculator portion of the ACT, but if there were, this would be on it probably. Okay. Addition, subtraction, multiplication. All right, number 10 combines the operations multiplication and subtraction. Addition has been involved the whole time anyway because we're simplifying. So let's work this one out, and then we'll get into the next part. All right, so we're going to take what order of operations, what should happen first? Okay, can I combine anything on the inside of those parentheses? No. So what do the parentheses indicate as an operation? Multiplication. Which one happens first, multiplication or subtraction? Multiplication. I've got to multiply these two wonderful pieces in the front here before I can do any subtraction. So 1 times 9 is 9. 3i, 63i, plus 21i squared. Minus 21. Negative 12 plus 66i minus 4 plus 2i. Now I can do that subtraction. Negative 12 minus 4, negative 16. 66 minus 2, 4i. And again, take that, punch it into the calculator just like it's written. It's going to crank out the same answer to that. Okay. Cranks out the same answer. Okay. Questions about what we've done so far? Okay. All right. Next thing is some special multiplication that happens. Over. Walks up there, setting down. Okay. So complex conjugates is what this is called. All it means is it creates the factors like a difference of squares, but with complex numbers. Complex conjugates, 8 plus I, the complex conjugate to that is 8 minus I. Just change the sign in the middle. That's all it does. And what happens when you multiply those two things together is quite nice. 8 times 8, 64, right? Minus 8i plus 8i minus I squared. And then we simplify. What happens to the 8 i's in the middle? Yeah, one's a positive, one's a negative, so they go away. What happens to I squared? Turns into positive 1. When I multiplied 8 plus I by its complex conjugate, it removes all of the imaginary part. That's what a complex conjugate does. It gets rid of the imaginary part. That's kind of important. Kind of important. There's some other things that happen when that when we get into larger degree polynomials. There's some interesting things that happen there. All right. Number 12. Same idea. 4 or 5 minus 4i. The complex conjugate to that is 5 plus 4i. Just change the sign in the middle. So if I ask you to find the complex conjugate, all you got to do is change the sign in the middle and you're done. Okay. Now, if you got to multiply them together, you should know that the I parts go away. And then when you multiply negative 4i to both of those, that's going to be negative 20i. And that would be negative 16i squared. The 20i's in the middle go away. End up with 25 plus 16, which is 41. Not a hard thing, just an extension. It's a special product is all it is. It's like a difference of squares is a special way of factoring. This is just a special way of multiplying those. Okay, nothing too bad about that. Now, the next thing, we've done addition and subtraction, we've done multiplication. Obviously, we got to do division next. Y'all can see it on the paper there. So division, this is something that's not normally on the non-calculator portion, but I'm going to show you how to do it by hand anyway. Just because it could show up. Technically, it's legal that they could ask you to do this on the non-calculator portion. So I want to make sure you've seen how to do that. But of all of the operations, this is the one that I would use the calculator on the most, just because it just takes time. It's not necessarily difficult work, but it just takes time. All right. The I cannot be in the denominator of a complex number. Remember, our standard form is a plus bi, not a plus b over I. That cannot happen. Okay, can't have I in the denominator when you get done. Okay, so we got to have that I either in the numerator or out to the side. So 10 over 2i, we want to simplify that by getting rid of the I that's in the denominator. Okay, and it's called rationalizing. Y'all remember doing that in geometry, where you had to rationalize the denominator? The whole idea of rationalizing has to do with rational thinking. The whole name of numbers is rational thinking. So if I took this ruler and I asked you to cut it into 2 equal pieces, could you do it? Yeah, it'd be pretty easy to do. It's a 12.5-inch ruler, so I could go to 6 1/4 inches and cut it right there, and it'd be perfectly in 2 equal sized pieces, right? If I told you to cut this into the square root of 3 pieces, what does that mean? If I said cut it in 3 pieces, could you do it? Yeah, you could measure it out and get, or take 12.5 and divide by 3, and you could get that. You could cut 3 equal pieces. But if I said square root of 3 pieces, that doesn't make sense, does it? That's not rational. That's the idea of it, okay? So when we have an I in the denominator, that's a square root of -1. And if I ask you to cut something that's 10 inches long into 2i pieces, or 2 times the square root of -1 pieces, does that make sense? No. But if I ask you to cut it into 2 pieces, that's pretty easy. You go to 5 inches and cut it in half. That makes sense. So if we can rationalize this, make the denominator a real number instead of a complex number, then it makes it a rational or a much simpler idea to think about. So that's what the idea of this is. So if you have a complex number in the denominator, or in this case, we have a purely imaginary number. So this is like the numbers from last Friday. Purely imaginary numbers. What part of that's the problem? The 2 or the I? The I. So here's what I'm going to do. I'm going to multiply by I on the top and bottom. What's I divided by I? Maybe here's an easier question that's very similar. What's 7 divided by 7? 1. Because it's the same thing on top and bottom, right? So I divided by I would be 1. What happens when you multiply something by 1? It stays the same. That's the key. It stays the same. It's the same number. It doesn't change the number that it is. What this is going to do is going to change how it looks. Okay? So rules for multiplying fractions. Top times top, bottom times bottom, right? 10 times I would be 10i. What's 2i times I? 2i squared. What do we know I squared really is? -1. So that makes this 10i over -2. Yeah, it puts the I out of the denominator. It's now in the numerator. We moved it. We didn't change the value because we changed it. We multiplied it by 1. I over I was 1. We didn't change the value of it. We just changed the way it looked. Okay? It's kind of like when you get the tub of Play-Doh, you get the whole tub, you can sculpt it into whatever you want to, but it's still the same amount of Play-Doh, right? Same idea here. We've got this fraction. We've changed the way it looks. We put it in a different shape, but it's still the same fraction. All right? So let's simplify that a little bit. What do 10 and -2 have in common? 2 goes into 10, right? So we can do that division there. 10 divided by -2 would be -5i. And we end up with a nice number that doesn't have an I in the denominator. It's purely imaginary. No complex part to that because we don't have a real portion of that. All right, let's look at number 14. What part of the denominator is the issue? The I. The 9 doesn't matter. We can have fractions with 9 on the bottom. If I ask you to take a ruler that was 9 inches long and cut it into 9 equal pieces, that's easy to do. Okay, so 9 in the denominator is not a problem, but I in the denominator is. So we're going to rationalize I over I. So that's 4i over -9i squared, right? So that changes that to a +9. So it's 4i over +9. Does that simplify like the other one did? No, 4 and 9 don't have anything in common. But we've made it have a good number on the denominator, a 9 instead of 9i. Okay, that's what we're after here. Okay, now number 15. Look at the denominator. Got that stupid I in it again. All right, we got to get rid of that. How did we get rid of it in 13 and 14? Multiply both top and bottom by I. On the top, we got to distribute I times 28 and I times -8i. It's a distributive property up top. So it's going to be 28i minus 8i squared. On the bottom, be 4i squared. What do we know the I squared stuff does? Changes the sign, right? So that's 28i plus 8 over -4. Now, here's where I got to get it into standard form. Remember, standard form is a plus bi, not written like a fraction, right? So when -4 is in the denominator, that means it's the denominator for the 28i and for the 8. So I'm going to rearrange it and split it apart into 2 fractions, and then try to simplify any of the fractions that will. Okay? Because this is the denominator under 2 things, it becomes the denominator of 2 separate things. That's the common denominator rule about that. Now, 8 over -4 becomes -2. 28 over -4 becomes -7. So I'm going to make that a -7i. Now, I don't do, I told you that doing division with the calculators where I use the calculator the most. I hadn't used it yet. I'll show you on this one just to make sure you know how to type this into the calculator. You don't make the easy mistake that could happen. So I'm going to go to the calculator. I'm going to type in the original problem. So parentheses around whatever's in the numerator, even though the problem didn't have it in it. Okay, the problem had 28 minus 8i. I put that in parentheses. You have to. If you don't, it's going to mess it up. Okay. And then I'm going to hit the division symbol. And then I'm dividing by 4i. So I'm just going to put parentheses 4i. Negative 2 minus 7i. Isn't that what we got by doing it by hand? Yeah. So that's definitely a lot quicker than doing it by hand, no doubt. It took us a good bit of scratch work to get that done by hand. Last semester, there wasn't one of these on the no calculator portion, but according to the standards and what they assess on the benchmarks, this could be on there. So knowing how to do it by hand is something that you are asked to do. It wasn't on the last one. The last one had addition, subtraction, and multiplication on it, though. So it's possible that they put a division on this one since they didn't do it on the last one. I don't know. So knowing how to do it by hand is important. Checking it with the calculator while we're doing it in class is a good thing. Try to make yourself try to practice a little bit by hand. Okay, don't just solely rely on that calculator completely. It's great, but it can kind of make us suffer a little bit. All right, let's look at 16. Let's try another one like that, and then we'll get to a tougher one with 17 and 18. All right, what do we need to multiply by? Just I. The bottom part has I on the bottom, so we got to get rid of that. It's a purely imaginary on the bottom. That's the key to knowing to just multiply by I, is because the denominator only has an imaginary number and it doesn't have a complex number on it. If it's got a complex number in the bottom, you got to do something different. Okay, so multiply top, got to distribute. That's going to be negative 8i minus 2i squared over 6i squared. That's going to be negative 8i plus 2i, or plus 2, excuse me, over negative 6. Rearrange it. And simplify. I rearranged it by just putting negative 6 under each term, and then put the real part in the front, the imaginary part in the back. Simplify the fractions. That's going to be negative 1/3 plus positive 3 over 2i. If you put the I with the 3 like this, that's the same thing. So I up in the top with the 3, or I out to the side. 4 over, it should be 4 over 3. 4 over 3. What that should be. So either the I goes up top with the 4 or out beside the fraction there. Okay. So with my calculator, if I wanted to check that, again, I'm going to put the parentheses around the stuff in the top. Negative 8 minus 2i divided by parentheses 6i. My calculator is set to give me decimal answers back automatically. How do I change from decimals to fractions in the calculator? Y'all remember how to do that? Math, enter, yeah, math fraction. And then there is the fraction version that I got there. So with a purely imaginary number in the bottom, we're going to multiply by I on the top and I on the bottom, if it's purely imaginary. When we get to the next problems, we've got a complex number in the denominator. And this is where that complex conjugate comes back in. Okay? The complex conjugate, we need the complex conjugate to the denominator. So what is the complex conjugate to 5 minus I? 5 plus I. So I'm going to multiply by 5 plus I on bottom and top. The reason I multiply that by 5 plus I on bottom and top is because 5 plus I divided by 5 plus I is 1, and multiplying by 1 doesn't change the value. It's just going to change the way it looks. Okay? So, distributive property up top, negative 10 minus 2i. On the bottom, it's distributive property twice. 5 times 5 is 25. 5 times I is positive 5I. Negative I times 5 is negative 5I. Negative I times positive I is negative I squared. What happens to the i's in the middle? They cancel out. That becomes a plus 1, right? So that's going to be negative 10 minus 2I over 26 when you simplify. And then we're going to split it apart again. 10 or negative 10 over 26 minus 2I over 26. And we're going to simplify those. We got 1 over 13I. That's our final answer. All right. If I type that in on the calculator to check it, put negative 2 in parentheses divided by parentheses, is it 5 minus I? Just type it in straight like that. Then I'm going to hit math, enter, to get it to change it to fractions. Boom. Same thing we got. I hope they put this on the calculator portion. They're not going to. They never do. But just straight up doing this kind of problem on the calculator portion, unfortunately. It's not much of a test if you make it that easy. All right, let's try number 18. Got an imaginary number up top and a complex number in the bottom. Okay, which one of those is the problem? The imaginary up top or the complex at the bottom? Complex in the bottom is the problem because we can't have that I in the denominator of our fraction. So we're going to multiply by the complex conjugate of 6 plus 2I, which, yeah, just change the sign in the middle. 6 minus 2I. Top part, distribute. 5I times 6 is 30I. 5I times negative 2 is negative 10I squared. On the bottom, 6 times 6 is 36. Minus 12I plus 12I minus 4I squared. I'm just distributing the 6, then I distributed the positive 2I. Cancel out the stuff in the middle. The top part's going to be 10 plus 30I. And on the bottom, it ends up being this being plus 4. So that's going to be 40 on the bottom. Split it apart. And simplify. So 1/4 plus 3/4 I. Again, calculator, parentheses, 5I, divided by parentheses, 6 plus 2I, and math, enter if you don't know that that's the same thing. Easy stuff. Calculator-wise, it's easy. I won't say that the other part's easy. Because if you miss multiply one thing or miss a sign, it's completely wrong. If you're doing it by hand, so you got to be careful of that. All right, so 19 and 20 both have a complex number up top and a complex number in the bottom. Which one is the problem?
The bottom.
The bottom. It's okay if there's a complex number up top. We cannot have a complex number in the bottom. So we've got to get rid of that by rationalizing with the complex conjugate, which is 2 minus I. It's always the conjugate of the denominator, not the numerator. Easy to get confused and do the wrong one. And I could imagine on a multiple choice test that they would have the answer. One of the answer choices would be doing it the right way. The other way would be doing it with the conjugate of the numerator. You know that that's how they come up with answers to, or if you don't know, how they come up with answers to multiple choice questions is not random number generators. It's what are the ways you could do this wrong? And so your answer choices, there's always one of them that's just out there in left field. It probably is a random number, but 3 of the 4 that you have to choose from are always answers you could get if you did the problem wrong. Okay. And then the fifth one is the correct answer. All right, so let's work it out here. Top part, 7 times 2 is 14. 7 times I is negative 7i. 3i would be plus 6i. And then 3i times negative I would be negative 3i squared. So just distributing on top. Same thing on the bottom. 4 minus 2i plus 2i minus I squared. A lot of simplifying to do on this one. The bottom part's the easy one, so that's the one I want to do. So it's going to be 5 on the bottom. And then negative 3i squared becomes plus 3. So it's going to be 17 minus I, minus 1i or I. Split it apart. 17 over 5 minus 1 over 5i. That is truly standard form for a complex number. If you're unsure, parentheses 7 plus 3i, close parentheses, divided by parentheses 2 plus I. Math, enter. Boom. Same thing. Number 20 is no different. The complex conjugate is what? 2 plus 4i, do your multiplication. We're not going to work yet. We've done enough of those. All right. Next. Organization of numbers. So this goes back to what we did Unit 1. This is back January. First thing y'all hated the most probably was, and some of you hated it because you got everything else right on the test except for this part. So organize the numbers. So we're going to refresh ourselves on that. So you got another box here. This larger box that we have here is the complex number system. So this is the complex. And we use a C as the abbreviation for that. Now, the little circle that's outside in this box, this is just the purely imaginary numbers. Okay, so that's the things that just have an I on them. Okay, so this is pure imaginary. And we just abbreviate that with a lowercase I. Lowercase I. Remember, we got other stuff that has the uppercase I. Now, that is the addition to the box that we drew back in January. You probably I know you remember it so vividly, this box that we drew in January with that. No, I don't expect you to remember that because we don't do it very often. But it does come up, and it is something we've got to think about. So this box over here that's inside, that's the one we had in January. The bigger box is the real number system. And then this circle is the irrational. That's right. And remember, it had the capital I as its abbreviation. So capital R for real numbers, capital I for irrational, lowercase I for purely imaginary. Okay, that's where that comes from. Now, over here we had these buckets of different kinds of numbers. The largest circle, the largest bucket, was rational numbers. Remember, the abbreviation for rational numbers was Q. Is it quotient? Inside of the rational numbers, remember, rational numbers just means you can write me as a fraction. That's what rational numbers means. We had the integers. And they abbreviated it with a Z for some reason. We didn't know why. That's what they used. I was already taken by irrational. And there's no reasoning with someone who's irrational, right? So he had the I. I'm not going to argue with you. Okay. And then inside of integers, we had whole numbers. So what are whole numbers? Let's review that a little bit. No decimals, no fractions. Natural numbers include, well, okay, you said natural numbers. What the heck's a natural number? What's a natural? Oh, like the numbers they count with, right? What we naturally learn to count with when we're kids, right? With 1, 2, 3, 4. So the natural numbers is this smallest circle on the inside. Whole numbers is all of the natural numbers, and then you just add a 0. So the idea of a 0. And then integers is all of those natural numbers, 0, and then those natural numbers again, but what in front of them? Negative sign. Okay, so all the negative natural numbers, or all the natural numbers made negative. And then rational numbers means, okay, now we're going to get everything that's between those that can be written as a fraction. Okay. Irrational numbers are those things in between those that cannot be written as fractions, like square root of 3, square root of 5, square root of 7, that sort of idea. Anything else? Real numbers. What are some numbers that would be real numbers that are not irrational and not rational? That's a pretty large question. I don't know if you guys can answer. I'm not sure I could answer that in a clear way that would be easy for you to understand. Because pi is technically irrational because it continues and goes forever. But there are some mathematicians that say pi is not irrational, that it is just a real number, because pi could be represented as a fraction if you think in terms of the circumference formula of it. Circumference equals pi times diameter, so you could write pi is equal to circumference divided by diameter, and then they say, oh, then that makes pi a rational number, and then the argument continues and it keeps going forever there. But that would be a hard question to answer there. But reviewing those things, though, we just added the complex box and the imaginaries bucket that's on the outside. That's what we've added. Now let's classify some numbers real quick. Square root of negative 64. The directions say simplify, then name all the sets that number belongs to. So we're going to simplify first. What's the square root of negative 64 turn into? And something else. Oh, that's got an I on it. So there's the simplified version. Now let's classify it. It's imaginary, and if it's imaginary, it has to be complex. Imaginary and complex. 10i times negative 2i. Negative 20i squared, which makes it what? Positive 20. Ooh. What kind of number is that? It's a natural number. It's one of them we learned to count with, right? I think you got to be able to count to 20 before you go to kindergarten now. So if it's a natural, it's also a whole, which is also an integer, which is also rational. It's also real. Rational, I should have put a Q there, sorry. Real, and if it's real, it's also complex. Remember the bigger box we've added in there. That complex box has the real number box sitting inside of it. Okay. Think of it so it's not imaginary though. Simplified version. The I'd put irrational there. I shouldn't have put, should be Z for integer. Sorry. That's what that meant. That said integer and wrote I. My brain was thinking first letters. Sorry about that. So 20 is natural, whole, integer, rational, real, and complex. It's a lot of things. All right, let's simplify the square root of 1/9. Oh, dear. Remember we split that apart? What's the square root of 1? What's the square root of 9? All right, it's 1/3. Simplifies to be 1/3. What kind of number is that? It's a fraction, right? So it's a rational number, which is Q. And if it's rational, it's real. And if it's real, it's complex. Yeah, y'all love this part. It's part of the game. We got to play it. All right, number 4. Simplify that. 15 minus 9 would be 6. Negative 8 minus negative 3 be negative 5i. So there's the simplified version. What kind of number is that? Nope. Not imaginary. It's got a 6 on it. If it were imaginary, it'd just be negative 5i or something like that. So it's got the 6 on it, so that makes it complex. And that's all it is complex. I don't know either. Maybe we need to get a bunch of boxes and buckets and play a game or something. We have time for it. Well, good thing is there's not much of it on quizzes and tests. All right. Number 5. Let's go ahead and simplify that. 9 times 4 is 36 plus 20i minus 9i minus 5i, or yeah, 5i squared. Simplify. That's going to become plus 5. 36 plus 5 is 41 plus 11i. There's the simplified version. It's all it is complex, nothing more. I to the 41st power. So this takes us back to what we did Friday. Remember how we simplified that? How do we do that? Divide 41 by 4. Goes one time. Bring down the 1. Oh, doesn't go any. Got a remainder of 1. Remainder of 1 means that it's the same thing as I to the first power. Whatever that remainder is, remember, is the new exponent. That was the trick. And I to the first power is square root of negative 1, but what kind of number is that? It's imaginary. And if it's imaginary, it's got to be complex. Purely imaginary, though, because it's just a 9. Or just a number with a 9. Bless you. All right. Number 7. What's it mean to cube negative 2i? Yeah, multiply it out 3 times. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. I to the third. When I square I radical 7, that's going to give me I squared times 7. Remember when you square a square root, what happens? Square root goes away. And then we multiply that together. Negative 8 times 7 is negative 56. I to the what power? 3 plus 2 is 5. And 5 divided by 4 goes one time with a remainder of 1. So that's going to be negative 56i, which is imaginary and complex. Doesn't get any different than that for examples 8, 9, and 10. All right. Last page. Go to that properties page, and we'll talk about those real quick. Commutative property. What does commutative property do? Moves it around, gets the same answer, right? So it'd be like 3 plus 4i is the same thing as 4i plus 3. Just change the order. Commutative property of addition. Just change the order. That's all it does. Associative property. What does it have in it? Parentheses. Always has parentheses in it. So example of that might be something like 2 times bracket 3 times parentheses 4 plus 5i. We'll make it really fancy. But if I rearrange that to 2 times 3 times 4 plus 5i, it doesn't change the order in which I could do the problem. It just changes the what's in parentheses part. I changed these two being in parentheses to the front two being in parentheses. That's associative property. Changes what's in parentheses. That's what the associative property does. Commutative property changes order. Associative property changes what's in the grouping symbols. Distributive property with complex numbers would be something like 5 times 6 minus 7i is equal to 30 minus 35i. Straight up distributive property. We've been doing that all day. Nothing new. We know what that means. Identity property. What's an identity property of multiplication? Times what? Times 1. Identity property of multiplication is taking a complex number or imaginary number times 1. The identity for multiplication is always times 1. What's the identity for addition? Plus 0. Yeah, that's right. Plus 0. Good job. Inverse property of addition. So what would be the inverse, the additive inverse to 3 minus 8i? What could I add to it and get 0? Because that's what the inverse does when addition. It'd be 8i or negative 3 plus 8i. Is that what you said? Okay. I'll write it how you said it. That's plus 8i. Opposite sign. So the inverse for addition is opposite signs. Inverse for multiplication is what's another name for multiplicative inverse? Reciprocal. That's the other word that we used most of the time. It's what we use most of our life is reciprocal instead of multiplicative inverse. Mostly because I think I can't say multiplicative inverse very well. Why I use reciprocal more. All right. Recognizing the properties. We'll just talk about these. 16. What did they do with the 2i? They multiplied it to individual pieces, which is what property? Distributive property. They distributed that to both pieces. Okay, so distributive property. 17. 1 over 3i times 3i. What's 1 over 3i compared to 3i? They're inverses. They're reciprocals of one another. So that's a multiplicative inverse or inverse property of multiplication, whichever way you want to write that. Or reciprocal. I would even take that on that one. What happened to number 18? What changed? What got switched around? What do you mean? Yeah, stuff inside of the parentheses changed, which is what property? Associative. Changes what's in parentheses. So this would be an associative property. Okay. What is number 19? What did they add to it? On the left side. Adding 0 is the additive identity. It's the identity property of addition, is what that is, because you're adding 0 and it doesn't change it. Gives you back the same thing. Number 20. What changed about that one? Yeah, they put the 8i in the front this time, so they didn't change what was in parentheses. Parentheses had negative 6i times 2i. This one's got the same parentheses, but the order's different. So what property is that? Commutative property. Commutative property. 21. Non-identity. Inverse. Inverse is going to equal 0 with addition. It's an additive inverse. The identity, you're going to add 0. That's where the difference is. Okay. Let's skip on down there to 24 about the closure property. That's the one a lot of folks struggle with. Closure property. What does it mean to be closed on a set of numbers? Yeah, whatever you start with is the kind of number you end up with. So number 24 says a set of complex numbers is closed under addition. So if I add two complex numbers together, do I get a complex number back? Can I come up with an example that does not? Think back to our chart. Complex numbers is the biggest set, right? So every number falls into that, right? It doesn't matter what kind of number we start with. That'd be true. Yeah, complex numbers is closed under addition because you're always going to, every number that you have to classify, when you go to classify numbers, you need to put C on all of them because they're all complex. Every number is complex. Okay. 25, the complex numbers is closed under division. So if I divide two complex numbers, do I always get complex numbers back? Again, complex numbers, the biggest set. So no matter what I do when I divide them, I'm going to get a number back of some sort, but it's the biggest set of numbers. So it's got to be closed under division too, because you're always going to get complex numbers back. 26, complex numbers are pure imaginary numbers. Okay, so they put a little restriction on the end there. They said complex numbers are pure imaginary numbers. All complex numbers are pure imaginary. Is that true? No, that's false. Definitely. Give me an example. Okay, yeah, just any number, 3. A good number. I got another one, 3 minus 2i. That's not purely imaginary. It's complex though. 1/5. Anything. You can't, if you write a number down there that isn't just something I, then you got that one right. 27, a number cannot be both irrational and complex. Is the irrational bucket inside of the complex box? Yes. So that would be false. Take, for example, the square root of -7. That's I radical 7, isn't it? That's definitely a complex number, isn't it? 28. Product of a real number and a complex number is a real number. If I multiply a real number times a complex number, do I get a real number back? Yeah, I'm gonna get a complex number. So here's a real number, 2. Here's a complex number, 4i. 2 times 4i is 8i. And guess what? That's not a real number. That's a complex number. Technically, it's a purely imaginary number, but it works there. So a lot of stuff here. Got about 15 minutes left here.